Hi, my name is Jim, and what we're going to do today is take a customer's request for a circuit and see if we can design a comparator to meet those requirements. And what the customer wants is a circuit with a threshold of 2.6 volts and 2.9 volts, and we're going to let our VN be a 5 volt sine wave, and the output the customer wants is an inverted design, which means when the sine wave is more positive, then the output will be negative. And realistically, this does not have to be a sine wave. It can be any waveform that crosses the thresholds. So to start with, in this here, it kind of looks like it's going to be intimidating, is we're told what the extremes are. Here we have 2.6 volts, and here we have 2.9 volts. And the first thing we have to do is find the center of our hysteresis curve. So to do that, we'll just find the arithmetic, take the arithmetic mean of it, which is 2.6 plus 2.9 volts divided by 2 gives us 2.75 volts. So that'll be the center point right there. Now, once we know that, let's just trace this out and see if it makes sense to us. If the input is positive, this will be up here, and our input is going more positive, meaning down here, this is the input moving toward 5 volts, and we reach a point of 2.6 volts, we want the output of this to change. And then as the sine wave continues, up through here, the output is just going to go and remain at negative 10 volts until the input signal now begins to drop. And when the input signal drops and hits 2.9 volts, then the output is going to go high and stay high through the cycle until it repeats again. So I'm just tracing what the hysteresis curve would be doing as the sine wave is going through multiple cycles. So once we know the center here, we can kind of design a circuit. And what I'm going to do here is set up an offset, which is going to take our input voltage and translate that down and allow us to do comparisons relative to 0. Now, this is the second approach for me. What I tried before was feeding something into this input, and what I found with that design is it failed because there was no solution to the equations. Oh well, time to back up, figure something new out. So if I make this 2.75 volts, is what I can kind of do is reference right to the middle of this point. And I'm thinking that should work. So to help me see this, I'm going to segregate my resistor network from my op-amp, remembering that the load on the from the op-amp is very low at point Vx. And I'm going to let the input be its maximum value, its maximum threshold of 2.9 volts. And on the other side of my 1K, I'm going to have negative 2.75 volts. And what I want to do first is to find the total voltage across the two of these. Well, that's easy enough. 2.9 volts minus a negative 2.7 volts gives us 5.65 volts. Next, what I'm going to do is find the current flow, 5.65 volts divided by 2K. So we have to include both of those resistors when we determine the current flow. And that comes out to be 2.825 milliamperes. And next I want to find the voltage drop, DROP, across the 1K resistor. And that's simply going to be the current times the resistance, and that's going to be 2.825 volts. Now the reason the drop is important is because this does not reference ground. It anchors somewhere else. So to find out what that's going to be for our threshold voltage, and this is kind of what we want, is going to take our 2.75, our negative 2.75 volts, and add to it the voltage that we just determined, the drop across this resistor. So that's going to be this guy right here, and the drop is anchored here, and what that gives us is plus 75 millivolts here. Now that kind of makes sense because 2.9 volts from the standpoint of absolute value is a higher magnitude than 2.75 volts, so we'd expect this here to be more positive. So let's just check the other extreme and make sure everything's okay. If these values don't work out to be the same except for opposite polarity, I guess I'm going to have to come up with a third circuit. So now we're going to find Vx and let the input be the other threshold voltage. And I want to find our maximum voltage as I did before. So I'll take our 2.6 and subtract from it our 2.75 volts, which gives me a total voltage of 5.35 volts. Now I'm not dealing with any positive or negatives on this voltage because I'm using this diagram to assist me in determining that. In other words, I don't want to base this on the signs of the output when I can see in my mind's eye what it's supposed to be. Now, sometimes you have to do that, but not in this case. So anyhow, finding out what the current is, we have 5.35 volts divided by 2K again, and that'll give us 2.675 milliamperes. The drop across the 1K then is 2.657 volts, and Vx in this point is going to be our negative 2.75 volts, which is our reference voltage, plus our 2.675 volts, and that gives us negative 75 millivolts. So I'm pretty happy with that. Looks like this circuit's going to work. Now what I have to do is find R2, and most of the work is done, good thing. So what I'm going to do on this guy is several different approaches, but I'm going to push currents. So I'm going to let this equal 75 millivolts, select a value for R1 which is reasonable. Now I'm using 1K because it's a nice number. There's nothing wrong with 22K. And finding the current through this, I have 75 millivolts here. The 1K resistor gives me 75 microamps flowing down. Now, since this here is going to be 75 millivolts, this output is going to be, under this circumstance, 10 volts. And that basically is our starting point anyway. I should have mentioned that first, but it's okay. And the current's going to be flowing in this direction. Again, no loading of the op-amp. And my next mission is to figure out what the voltage drop is going to be across R2, and that's easy enough to do. I know the output is 10 volts, and this side of R2 is 75 millivolts. So if I subtract the difference, I end up with 9.925 volts. So far so good. I know the current I flowing through it, so I can do the math on R2. Divide the voltage, the 9.925 volts by 75 microamperes gives me 132.3 repeat kiloohms. So this is what the circuit would look like, which would actually meet the customer's requirement. Now, these values here are very precise to meet that, and realistically you'd be probably looking at 1% resistors and settling for close, or putting an adjustable in, making it precise. Now, so far the output of our comparator circuit has been plus or minus 10 volts, and that's really not going to work well with a 5 volt proc or a 3.3 volt proc, which most of them are these days. So comparators are set up so that you can use them with a single supply. And they're also set up so you can use them with, say, a 5 volt or a 3 volt microcontroller. So we're not going to get into that aspect of it because we don't have to. The design is exactly what we did here, except we're dealing with a unipolar supply. And then the output will be switching between 0 and some positive value, which to whatever circuitry follows it would be represented by a logic 1, and that's assuming positive logic. So we have a lot of variability here to work with contemporary components, but this is kind of the underpinnings of comparators, and I have to say they can be challenging. So if you're doing problems on this, take your time, think it through. The positive input's more positive than the negative. The output's going to be high, and that should be your guiding light. So that'll conclude for this topic, and thank you for watching.